Okay, now we're going to take a look at another problem. This one deals with work per time. So, I told you before that energy and work have a big limitation in that they have no time dependence. Well, one of the things that we found is power equals energy per time, or work per time is usually the better way of looking at it, because when you're trying to find the power of something, a lot of times it's a motor or something like that that's actually physically doing work. But you can also get it from time to time on energy, depending on how you're looking at it, because work and energy have a strong relationship to one another. Okay, what I want to know is the power of a car. Let's go with the Tesla Roadster. And I've got a situation where the power supplied to it comes from an engine, okay? And the engine has some power that I want to know. Well, one of the ways that I could find that out, or I could find the power that it uses to accelerate some. So one of the things that we usually keep track of to describe how fast or how powerful a car is 0 to 60 miles per hour data points. Normally we'll have a thing where we measure how long it takes for a car to go from 0 to 60 miles per hour. In this case, for the Tesla Roadster, that is 3.7 seconds. So this is something that we looked at before in one-dimensional kinematics to solve for accelerations. In this case, what I'm going to do is I'm going to take a look at my energy that's supplied in a given time. So if I look at my power, I've got a situation where how much energy do I get in a given time? Well, it converts that power, at least the main thing that we can keep track of, is going to be in velocity, into kinetic energy. And so we have kinetic energy final minus kinetic energy initial. Basically how fast it's going, or how much kinetic energy it has at the beginning of the time period versus the kinetic energy that it has at the end. We're going to divide that by the total time it takes. That should give us at least the power that's going into the velocity or the kinetic energy for this vehicle. All right, well, I'm going to do a quick conversion here where my initial velocity is 0 miles per hour, which is also 0 meters per second. It's going from rest. My final velocity is going to be 26.8 meters per second. That's 60 miles per hour converted to meters per second. So if you're not familiar with that, go ahead and run through that conversion. And so what we're going to do is we're going to find our kinetic energy final and our kinetic energy initial. Well, the initial should be pretty easy. P equals kinetic energy final, which is going to be 1/2 mv final, which is V1 in this case. V1 squared minus 1/2 m V0 squared. Well, V0 was 0, so this term just goes away, divided by our total time, which is 3.7 seconds. Extending this up some, the power that goes into speeding the car up is 1/2 m V final squared divided by the time. Well, 1/2. The mass of the Tesla Roadster, which I looked up, was 1,235 kilograms times V1 squared, which is 26.8 meters per second squared. That's going to be divided by my total time, which is 3.7 seconds. The power required to speed that car up to 26.8 meters per second in 3.7 seconds. If I evaluate that, I find that my power comes up to right at about 120,123. So 120,000 watts. A watt is a joule per time, or per second. I'm sorry, not per time, per second specifically. Joule per second equals a watt. We can see that we've got power is energy, which is in joules, and our time, which is in seconds. That gives us watts. Those are units of power. Okay, so this, said another way, the power is 120 kilowatts. When you actually look up the engine inside the Tesla Roadster, it'll tell you that the actual power, in fact, let me change colors on this, equals 185 kilowatts. Well, that's good, because it would be worrisome if it was less than 120. But what makes up this discrepancy? The engine can put out way more than the 120. It can put out up to 185, at least on average. So why can't I speed up faster than that? Well, because when they get these 0 to 60 data points, they're not doing them just by running the math. They're actually putting them out on the road and testing them on a track. And out in the real world, we have situations that we're ignoring right now, like air resistance. Drag is definitely going to cut into this when you're going up to 60 miles per hour. If you put your hand out the car window on the highway, you know that air pushes pretty hard on you. And then there's also things like friction and some other losses that come in. In fact, this is a pretty good ratio here. We've actually got a pretty good amount of the overall power that the engine can put out going into what we want, which is our kinetic energy. But this is one of the ways that we can actually get an idea of the power output of a car. This isn't the only way, but this is one way that we can go about it. We can look at how quickly it goes from 0 to 60 and see the type of power, the energy in the given amount of time required to get that car up and moving that fast. And then if we can account a little bit for friction or air resistance, we can probably get a pretty good estimate of what the actual power output of the motor is.